Welcome to Sleepy Space Facts, your nightly home for space facts for sleep. Dark matter explained, relaxing astronomy videos, and cosmic ASMR science. Tonight's episode drifts through the invisible, the silent substance called dark matter, the hidden mass that keeps galaxies from flying apart. Fall asleep to a calm, factual story of the universe's invisible structure, where stars shine, but gravity does the real work. Through peaceful narration and ambient sound, we'll uncover how dark matter forms the cosmic web, why we can't see it, and how it holds everything together from the smallest galaxy to the edge of time. Perfect for bedtime learning, deep rest, or slow stargazing. This is science that soothes as it informs, because even in the dark, there's beauty worth listening to. I hope this video isn't so interesting that it keeps you awake. But if it does, at least you'll fall asleep a little wiser. So, what exactly is holding galaxies together when there's not enough visible matter to do the job? Dark matter. The phrase itself sounds like something out of science fiction, mysterious, invisible, maybe even ominous. But in truth, it's the quietest and most patient part of the universe. It doesn't glow. It doesn't collide. And yet, its invisible weight sculpts the cosmos into the shape we see tonight. For nearly a century, astronomers have watched galaxies spin faster than they should. Stars hold together when gravity alone should scatter them, and entire clusters of galaxies drift as though guided by unseen hands. Each clue whispered the same thing: there's more out there than light can tell us. In this calm exploration, we'll drift from those first strange observations to the vast web of invisible filaments stretching between galaxies. We'll follow the evidence written in the bending of starlight and the afterglow of the Big Bang. Along the way, we'll meet the tiny hypothetical particles that might make up this dark mass and the quiet experiments, hidden deep underground, that are still listening for them. No equations tonight. No heavy jargon, just the slow, steady rhythm of a mystery that has shaped everything we know. As you relax and listen, imagine the universe as a great tapestry woven mostly from threads you cannot see. The stars are only the embroidery. The true fabric lies beneath, silent and unseen. The dark matter of space. In the quiet decades between the two world wars, when telescopes were still guided by hand and photography required patience measured in hours, a Swiss astronomer named Fritz Zwicky began studying a cluster of galaxies far beyond our own. It was called the Coma Cluster, a vast congregation of thousands of galaxies, each filled with billions of stars drifting together through intergalactic space. Zwicky was fascinated by its structure, but as he studied it more closely, something didn't add up. He measured the speeds at which the galaxies were moving, and they were racing around far too fast. According to Newton's law of gravity, the visible matter in those galaxies simply wasn't enough to keep the cluster together. The galaxies should have flown apart like sparks scattered by the wind. But they hadn't. They were still bound. Still orbiting within the cluster's gravitational grasp, the numbers told a strange story. The Coma Cluster appeared to weigh hundreds of times more than what its visible stars and gas could account for. Zwicky, with his sharp tongue and impatient brilliance, called this missing ingredient dunkel materie, dark matter. It wasn't meant to be poetic. He simply needed a name for whatever invisible something was holding everything together. His calculations were based on what's called the virial theorem, a straightforward principle in astrophysics that connects how fast things move within a system to how much mass that system must have. In simple terms, If galaxies move faster than expected, there must be extra gravity keeping them from flying away. Gravity, after all, only follows one rule. The more mass you have, the stronger your pull. Zwicky's observations implied that there was a vast amount of unseen mass providing the glue. At first, few people paid attention. Zwicky had a reputation for being, let's say, a little difficult. He once described some of his colleagues as spherical bastards, meaning they were bastards no matter which way you looked at them. Brilliant, yes. Diplomatic, not so much. But even if his personality grated on others, his math did not lie. The coma cluster really did move as if it were full of hidden weight. The idea of missing mass seemed too strange for many astronomers at the time. The universe was still thought of as a place made of visible things, stars, gas, dust, and planets. The notion that most of its substance might be invisible was almost unthinkable. Perhaps Zwicky had made an error in his measurements. Or maybe the light from distant galaxies was being distorted in ways they didn't yet understand. It was easier, and far more comfortable, to assume that the problem lay in the data rather than in the universe itself. Yet the numbers kept whispering the same story. The galaxies in the coma cluster were moving too quickly for their visible light to explain. Even if you added up every star, every cloud of gas, and every faint wisp of starlight, it still wasn't enough. Something else, something unseen, had to be providing most of the cluster's mass to picture it. Imagine floating in space, looking down upon the coma cluster. Thousands of galaxies gleam like lanterns drifting across a dark sea. Between them lies nothing but blackness. But that blackness isn't truly empty. It's heavy with something invisible, an unseen web that binds each lantern in place. If you could somehow strip away that hidden mass, the galaxies would scatter like sparks from a dying fire, leaving only emptiness behind. Zwicky's discovery planted a seed of doubt in the neat, luminous picture of the cosmos. For the first time, scientists were forced to consider that what they could see, the glittering stars and glowing nebulae, might be just the thin surface of something far greater. He couldn't know it then, but his lonely calculations were the first cracks in the universe's bright facade. Behind the light, a shadowed architecture was waiting to be revealed. It would take decades for others to notice it. And nearly a century later, humanity would still be trying to understand it. What Zwicky had stumbled upon wasn't a trick of measurement or a gap in data. It was a truth so large that it would reshape cosmology itself. The visible universe was not the whole story. The luminous galaxies that filled the night sky were only the decorations on a far grander structure. It's an oddly comforting thought that even in the darkness there is structure, balance, and hidden order. The coma cluster didn't need more stars or brighter light to stay together. It needed the quiet weight of the unseen, the gravity of something that asks for no attention, offers no glow, but holds everything in its place nonetheless. Fritz Zwicky didn't have the tools to see what that something was, only the courage to point out that it must exist. His data didn't reveal a new kind of star or planet. It revealed a new kind of ignorance, a reminder that the universe still had secrets it wasn't ready to share. And as the decades passed, astronomers began to notice the same strange imbalance in other galaxies too. The whisper that began in the coma cluster grew louder, echoing across the cosmos until scientists could no longer ignore it. What Zwicky saw in that cluster of drifting lanterns was not an anomaly. It was the first hint of a hidden order shaping everything we see. A whisper had become a pattern. In the middle of the 20th century, astronomy was undergoing a quiet revolution. New telescopes were turning their gaze outward with more precision than ever before, and astronomers were beginning to map the movements of individual stars within galaxies. Among them was Vera Rubin, a calm, meticulous scientist who loved the night sky and the quiet rhythm of data as much as she loved the galaxies themselves. She wasn't interested in fame or grand theories. She simply wanted to understand how galaxies moved. Rubin's work focused on spiral galaxies, those graceful, swirling disks of stars that look almost peaceful from a distance. But behind their beauty lay a puzzle that would change how we see the universe. When a galaxy spins, its inner regions, the stars closer to the center, should move faster than those on the edges. That's how gravity works on large scales. The farther you are from the mass in the middle, the weaker the pull and the slower your orbit should be. It's the same reason planets in our solar system behave the way they do. Mercury, huddled close to the Sun, whips around it in a tight, rapid orbit. Neptune, drifting far out on the edge, takes over 160 years to complete a single lap. The rule is elegant, predictable, and comforting. The farther you are, the slower you go. But when Rubin and her collaborator Kent Ford began carefully measuring how fast stars moved around their galaxies, the data refused to behave. They used the Doppler shift, the subtle change in light's wavelength as objects move toward or away from to trace the speed of stars at different distances from the galactic center. The results were stunningly consistent and completely unexpected. Instead of slowing down, the stars on the outskirts of galaxies were moving just as fast as the ones near the middle. The rotation curves, graphs showing speed versus distance, didn't fall off like a gentle hill. They flattened out, stretching horizontally across the chart as if the outer stars had decided to ignore Newton entirely. Galaxies, it seemed, were great at ignoring instructions to slow down. Rubin described her findings with scientific restraint, but behind the data was something astonishing. According to the laws of gravity, these galaxies should have flown apart long ago. The visible mass, the stars, dust, and glowing gas simply wasn't enough to keep the outer stars bound. Yet the galaxies held together beautifully, rotating in steady defiance of expectation. Something unseen had to be adding extra gravity, not just a little bit, but several times more than all the visible matter combined. Whatever it wasn't emitting light, wasn't colliding like normal matter, and wasn't hiding behind clouds of dust. It was there, invisible but undeniable, forming a vast halo around each galaxy, reaching far beyond the luminous edge. To picture it, imagine a record player turning slowly in the dark. You can see the glowing dots near the center spinning swiftly, but even the faint ones near the edge circle with surprising speed, refusing to drift behind. The music in this case, gravity, plays evenly from center to rim. The galaxy is the record, and the invisible dark matter halo is the hand keeping the rhythm steady. Rubin's data wasn't just a fluke of one galaxy. As she studied more and more of them, from tiny dwarfs to enormous spirals, the same pattern emerged again and again. Flat rotation curves, vast outer stars, hidden mass. What began as a single anomaly turned into an undeniable rule of nature. Her results were met with skepticism at first, as most revolutionary findings are. The idea that galaxies might be surrounded by huge cocoons of unseen matter felt outlandish. Perhaps there was a problem with the data, or maybe the laws of gravity themselves needed tweaking. Rubin, however, was thorough to the point of perfection. She repeated her measurements, refined her instruments, and expanded her sample until the evidence became unassailable. The galaxies weren't misbehaving. They were revealing the universe's hidden architecture. What made Rubin's work so remarkable wasn't just the precision of her science, but the quiet grace with which she carried it out. She didn't frame her discovery as a cosmic upheaval. She treated it as a natural part of learning, another layer of truth waiting patiently for us to notice. She once said, "We are still groping for understanding." It wasn't a confession of confusion, but of wonder. The implications were enormous. If every galaxy needed an invisible halo of dark matter to hold itself together, then dark matter must be everywhere, woven through the cosmos, anchoring every cluster and filament. It wasn't a rare oddity. It was the dominant form of matter in the universe. The bright stars and glowing nebulae we admire are just the frosting on a vast, invisible cake. Vera Rubin didn't claim to know what dark matter was, only that it must be there. Her quiet determination reshaped modern astrophysics. The universe was suddenly heavier, stranger, and more beautiful than anyone had imagined. For every twinkling point of light, there was an ocean of unseen mass making sure it stayed in place. Her discovery also highlighted something profound about science itself. Sometimes the universe doesn't shout its secrets, it whispers them through patterns that refuse to fade. A flat line on a graph can be as earth-shaking as a supernova, if only we have the patience to listen. Rubin's galaxies continued to spin, calm, elegant, and slightly rebellious, as if reminding us that light is not the only way to measure reality. Behind every star is the quiet pull of the invisible. And behind every discovery is someone who noticed when the numbers didn't behave. When Vera Rubin passed away in 2016, the scientific world mourned not just the loss of a brilliant mind, but the gentle curiosity she embodied. Her work didn't merely confirm the existence of dark matter, it transformed it from a vague idea into a cornerstone of cosmology. She showed that even in the grand, impersonal scale of the universe, progress begins with the simple act of noticing something small. A graph that refuses to tilt. A star that spins too fast. In the end, her galaxies kept their rhythm. They turned unhurried and unbothered, guided by invisible hands. Each one a reminder that the universe's greatest forces are not always the ones we can see. The light shows us beauty, but the dark reveals truth. And in that balance, between brightness and shadow, lies the quiet heart of the cosmos, spinning forever through the night. Gravity is a little like a gossip in the cosmos. It cannot keep a secret. No matter how invisible something is, if it has mass, gravity will tell on it. It bends light, tugs on stars, and leaves unmistakable fingerprints wherever it acts. You can hide from the telescope, but you can't hide from gravity. Every object with mass curves the fabric of space around it. Einstein's general theory of relativity showed that gravity isn't a force pulling things from afar like a string. It's the shape of space-time itself. A star, a planet, or even you at this very moment are all pressing gently into that cosmic fabric, warping it ever so slightly. The heavier something is, the deeper its indentation becomes. When light travels through this warped terrain, it bends and twists along those curves not because it wants to, but because the path itself has changed. This is why, even though dark matter doesn't shine or reflect, we can still see where it hides. The light from distant galaxies is stretched, bent, or even duplicated as it passes through regions filled with invisible mass. Astronomers can trace that distortion and reconstruct the unseen landscape behind it. It's like watching ripples on a pond and knowing something large is moving beneath the surface. even though the water itself remains opaque. Gravity gives dark matter away every time. When stars move too quickly, when light bends in unexpected ways, or when galaxies cling together tighter than their visible mass allows. Gravity is whispering the same thing. There's more here than meets the eye. To make sense of this, picture the universe as a vast river system. The glowing stars and galaxies are the shimmering reflections you see on the surface, beautiful but superficial. Beneath that glossy calm flow powerful unseen currents, the gravitational influence of dark matter. You cannot dip your hand in and feel it, but everything you see on the surface moves because of it, for all its influence. Dark matter is extraordinarily well behaved. It doesn't crash into itself, doesn't spark or flare, and doesn't absorb or emit light. Physicists call it meaning that while ordinary matter, the stuff that makes up you, me, and stars bumps and interacts through electromagnetic forces, dark matter glides through itself and through us as though we weren't even here. It experiences gravity and, as far as we know, little else. If dark matter did interact strongly with itself or with light, the universe would look entirely different. Galaxies might glow with unexpected radiation, or their shapes would distort and clump in ways telescopes would easily detect. But they don't. The night sky is as serene as ever, its darkness pristine, which tells us that dark matter remains aloof from the chaos of ordinary matter. This strange detachment also explains why dark matter formed the backbone of the cosmos. In the early universe, when everything was hot and crowded, normal matter couldn't settle down. Photons, particles of light, kept scattering off charged particles, stirring everything like a cosmic soup. Dark matter, however, stayed cool and indifferent, unaffected by light. It began gathering quietly under its own gravity, forming the first clumps, the seeds of future galaxies, when the universe finally cooled enough for ordinary matter to calm down. It fell into those dark matter wells like sand settling in the grooves of a riverbed. In this sense, dark matter acted like a silent architect. It didn't build galaxies by hand, but it shaped the terrain on which they would rise. Without it, the universe might still be a thin fog of gas and radiation, bright but empty. The irony, of course, is that gravity itself is the weakest of all the fundamental forces. Yet over cosmic distances, it becomes the most dominant. It's the patient sculptor, the one that never stops carving. Over billions of years, its gentle persistence rearranges stars, clusters, and entire galaxies into patterns we can see from across time. And every one of those patterns carries the subtle trace of the dark. Sometimes the universe reveals these traces dramatically. When two clusters of galaxies collide, their visible gas clouds crash together and slow down, heating up into bright X-ray emitting knots. But the dark matter halos pass straight through one another, unaffected. The galaxies and gas pause for a moment, but the dark matter continues its dance, indifferent to the commotion. The result is a cosmic separation of light and gravity, one of the clearest signs that dark matter is real and that it plays by its own quiet rules. For astronomers, these moments are like catching a glimpse of invisible currents beneath the glassy river. The galaxies drift and swirl, the light bends and stretches, but the pattern always points back to the same hidden hand guiding it all. Gravity has written dark matter's signature across the sky, and all we have to do is learn to read it. It's remarkable to think that everything we know about dark matter comes not from seeing it directly, but from watching how it moves the things around it. Imagine trying to learn the shape of an animal you can't see, only by studying how it stirs the grass. Over decades, astronomers have pieced together a portrait from these gravitational hints. Dark matter forms halos around galaxies, connects them with invisible bridges, and holds the universe's structure in place. This invisible mass doesn't break the laws of physics, it completes them. Without it, gravity's equations would predict chaos. Stars would drift apart, clusters would dissolve, and galaxies would never form. With it, everything gains coherence, as though an unseen hand steadied the spinning record of the cosmos. So, while light may be the painter that colors the universe, gravity is the pen that sketches its outlines. Every curve, every orbit, every gleaming spiral we admire is drawn upon a framework shaped by the unseen. If you trace those lines far enough, you find that they connect into a vast, interlocking structure spanning the cosmos. Delicate yet immense, gravity, patient and ever honest, has revealed the shape of what light could not. The invisible doesn't hide from us. Out of malice, it simply doesn't need to shine to be real. It moves the galaxies, bends the light, and writes the architecture of everything that exists. If gravity is the pen, then the universe has drawn a web, an intricate, invisible masterpiece stretching through the dark, binding all things together in silence. When astronomers began to map the universe in 3 dimensions, they expected to find galaxies scattered roughly, evenly through space, perhaps clustering here and there, but generally spread out like grains of sand. Instead, what emerged was something astonishing. A grand, interconnected structure stretching across billions of light years. It looked less like a random scattering and more like a vast network, delicate and complex, woven from invisible threads. This immense pattern became known as the cosmic web, and it is quite literally the skeleton of the universe. The glowing galaxies and clusters of galaxies trace its filaments like beads on invisible strings, while between them lie immense voids, vast regions of almost perfect emptiness where hardly a single galaxy resides. To see the web is to glimpse the quiet architecture of creation, the dark scaffolding upon which all the light of the cosmos hangs at first glance. It's difficult to imagine how such structure could have formed. The early universe was nearly uniform, a smooth, hot soup of particles and radiation with only the tiniest ripples in density, variations of 1 part in 100,000. Those faint ripples were like the seeds of everything to come, where there was just a little more matter than average. Gravity began to gather it slowly and patiently, drawing it into denser knots. Over billions of years, those knots grew into the filaments and clusters we see today. Dark matter was the quiet builder behind it all. Ordinary matter, the kind that glows and forms stars, was too busy interacting with light in the universe's early days. It was hot, restless, and easily scattered by radiation. Dark matter, on the other hand, doesn't care about light. It simply moves under the influence of gravity. It began clumping together long before anything visible could follow. Once the dark matter had formed its invisible web, the gas and dust of ordinary matter flowed into those channels, pooling and cooling until the first stars ignited. The result is an intricate balance of light and shadow, luminous galaxies shining along the dense filaments of unseen matter, surrounded by vast empty voids. These filaments stretch across unimaginable distances, some spanning hundreds of millions of light years. If you could somehow step outside the universe and look down on it, it might resemble the neural network of a brain, or the branching roots of a tree glowing faintly against a black canvas. Astronomers often describe the web using words borrowed from biology or geology. Filaments, nodes, clusters, and voids. The filaments are the long strands connecting everything like cosmic highways. The nodes are intersections where filaments meet the densest regions where galaxy clusters form. The voids are the dark spaces in between vast cosmic deserts that make up most of the universe's volume. It's a little like foam or the bubbles in a rising loaf of bread, except the bubbles here are empty, and the walls between them are made of galaxies. To study this grand design, scientists rely on large-scale galaxy surveys sweeping the night sky to measure the positions and distances of millions of galaxies. When plotted in 3 dimensions, the picture that emerges is breathtaking, not a random spray of points, but an elegant tapestry of structure. Each filament hums with gravity's quiet pull. Every void whispers of balance. But the most striking thing about the cosmic web is that its shape can be reproduced almost perfectly using computer simulations. These models, built on what's called the lambda cold dark matter framework, start with simple physics, the expansion of space, gravity, and the presence of dark matter that moves slowly and interacts weakly. From those humble ingredients, a digital universe blossoms in these simulations. Dark matter is represented by millions or billions of particles that attract each other gravitationally as the virtual universe expands. Over time, tiny clumps merge into larger structures, forming long filaments and dense nodes that look astonishingly similar to what telescopes observe in the real sky. It's one of the great triumphs of modern cosmology that with a few key ingredients and the patient hand of gravity, the universe naturally weaves itself into a cosmic web. The lambda in the model represents dark energy, the mysterious force driving the universe's expansion to accelerate. Cold means that dark matter moves relatively slowly, allowing it to clump together instead of zipping around too fast to form structure. Together, these 2 invisible components, dark matter and dark energy, make up about 95% of everything that exists, while the stars, planets, and gas we can see make up only the remaining 5. In other words, the cosmos we know is just the faint shimmer outlining a vast unseen design. It's a humbling realization. The grandest patterns in the universe are drawn not by light, but by the absence of it. Every glowing galaxy is just a lantern hung on the framework of the dark. The cosmic web is a masterpiece, painted in reverse, its true lines defined by what we cannot see. There's a quiet elegance to how this structure balances emptiness and fullness. The filaments are narrow and dense, but the voids between them are immense. The universe, it turns out, is mostly empty, but not meaningless. Those empty regions allow the dense ones to exist, just as silence gives shape to music. Without voids, the web could not breathe. Without the dark, the light could not shine. Astronomers have even found that the web's filaments influence how galaxies spin and grow. Galaxies tend to align themselves along these invisible threads, their spins and orientations shaped by the flow of matter through the network. It's as though the entire universe shares a subtle choreography, every galaxy moving to the rhythm of a gravitational symphony that began billions of years ago. To imagine this, think of the veins in a leaf, or the filigree of frost on a window. Each branch, each curve forms naturally, following simple physical rules repeated over and over again. Gravity does the same on a cosmic scale, turning chaos into order with nothing but patience and time. There's even a kind of quiet poetry to the voids, the enormous, almost perfectly empty regions between the filaments. Some of them are hundreds of millions of light years across, containing fewer galaxies than you can count on one hand. These cosmic deserts are so empty that if you placed the Milky Way inside one, you might never find another galaxy within the observable horizon. And yet they're not barren in a sad way. They're peaceful, vast pauses in the composition of the cosmos from the outside. The web appears calm and timeless, but it's slowly evolving. Galaxies continue to fall along the filaments, merging and growing heavier. The voids expand, gently pushing the filaments farther apart as the universe itself stretches. Over billions of years, the cosmic web will thin out, its threads elongating until distant galaxies fade beyond sight. The pattern remains, but the lights grow dimmer. Even so, for now, it's a sight of extraordinary beauty, galaxies shimmering like lanterns along invisible bridges. Clusters glowing like city lights connected by highways of gravity. The cosmic web is the ultimate expression of order emerging from chaos. The universe finding harmony in the dark. When astronomers look at this structure, they aren't just mapping matter. They're reading the universe's autobiography. Each filament, each void tells the story of gravity's slow, unbroken work, the same hand that guides planets, holds galaxies together, and bends the light of distant stars. If gravity is the pen, then this is the drawing of vast interlaced web where the visible universe hangs like dew on unseen strands. And though it's built from darkness, it gleams with the faintest light, a reminder that the hidden and the visible are forever entwined. The shape of the universe is not random, and its beauty isn't an accident. It's written in the quiet patterns of gravity and time, traced in light that travels across billions of years to tell us how the dark has shaped everything we know. From this vast structure, the light we see takes its cue, revealing the hidden web that holds the cosmos together. Light is supposed to travel in straight lines. At least that's what our everyday experience suggests. A beam of sunlight shines through a window and lands cleanly on the floor. A flashlight cuts through fog in a tidy cone. But in space, things are rarely so obedient. Out there, light can bend, twist, and even loop back on itself, not because it wants to, but because the very stage it moves through, space-time, is warped by mass. And in that bending of light, we find some of the clearest evidence that dark matter truly exists. This phenomenon is called gravitational lensing, and it's one of the universe's more elegant tricks. Imagine placing a glass bowl over a star. The light from the stars behind it warps, stretches, and curves into arcs. Some stars appear where none actually are, while others grow brighter or duplicate. In space, galaxies and clusters of galaxies act like that invisible glass bowl, bending the light from objects far behind them. To an astronomer, it's like looking through a funhouse mirror that happens to be very good at physics. When the gravitational lens is strong, say, a massive galaxy cluster, the effect is dramatic. Distant galaxies behind it can appear as long arcs or rings of light known as Einstein rings, named after the man who predicted the effect. These cosmic distortions allow astronomers to map the distribution of mass, including the dark matter that makes up most of it. By studying how light is warped, we can reconstruct a picture of the invisible structure doing the warping. It's worth pausing here because this is one of those moments where nature feels a bit poetic. Light, which cannot interact with dark matter directly, still reveals its presence by following the paths that dark matter carves through space. In a sense, the universe uses light as ink, sketching the contours of the unseen. Even when the lensing is weak, just a subtle stretching or shearing of many background galaxies, the pattern adds up. Astronomers can measure this weak lensing over huge areas of the sky, building a statistical map of where dark matter must be. It's a delicate science requiring immense care and precision. But the reward is a view of the cosmos that no telescope can see. Directly a map of gravity itself, one of the most famous and dramatic pieces of lensing evidence came from a system known as the bullet-clustered, two massive clusters of galaxies that collided around 150 million years ago. When scientists observed the aftermath, they found something deeply revealing. The hot gas that makes up most of the visible matter in the clusters had slowed down and clumped in the middle, glowing brightly in X-ray light. But the bulk of the mass detected through gravitational lensing had passed right through the collision, ending up ahead of the gas clouds. This separation between light and mass was astonishing. If gravity were due only to the visible matter, both the gas and the lensing pattern should have lined up, but they didn't. The lensing revealed that most of the cluster's gravitational pull came from something that didn't interact with gas at all, something invisible, collisionless and dominant. It was as if two invisible ghosts had drifted past one another while the visible debris lagged behind. The bullet cluster became a kind of smoking gun for dark matter, a cosmic experiment written across millions of light years. It showed that dark matter behaves differently from ordinary matter, gliding through collisions rather than heating up or slowing down. And because gravitational lensing traces mass regardless of what it's made of, it provided one of the clearest, simplest proofs that the universe's mass is not where the light is. Gravitational lensing also serves as one of the most useful tools in modern cosmology. It lets us weigh galaxies and clusters like cosmic scales, revealing the true heft behind the glow. When astronomers map lensing patterns across the universe, they can even test how structure has grown over time. Light that has traveled for billions of years carries snapshots of the universe's past, each distortion a small clue in a much larger puzzle. These measurements are now so refined that they can distinguish between different kinds of dark matter theories. Cold, dark matter, the slow-moving variety, produces the large-scale cosmic web we see in simulations. Warm or fast-moving dark matter would smear out that structure, leading to a different pattern of lensing. So, by reading the faint handwriting of light, scientists can narrow down what kind of invisible matter shapes the cosmos. And while the term lensing might sound abstract, it's surprisingly visual. Astronomers often publish breathtaking images showing galaxy clusters surrounded by arcs of blue or red light, distant galaxies distorted by the cluster's gravity. In some cases, a single galaxy is copied several times across the sky, its images arranged in a circle or stretched into shimmering streaks. Nature, it turns out, has been running its own telescope all along, and it's much bigger than anything we could ever build. There's even a delightful irony in all this. We use light to see the dark. The very thing dark matter refuses to produce or reflect becomes our greatest ally in uncovering it. Light's flexibility, its willingness to bend and curve, becomes a form of honesty. Wherever it deviates, we know something massive is pulling it aside. It's tempting to imagine the universe as full of invisible lenses, like panes of distorted glass scattered through space. Light from distant galaxies passes through these lenses on its way to us, subtly twisted by every clump of mass it encounters. By the time it reaches Earth, the light carries a layered story of gravity, distance, an invisible structure the night sky we see is not a perfect window, but a mosaic of distortions, a portrait painted through curved glass. And yet this bending of light is what makes astronomy so rich. Without it, we'd have no way to map the dark. Every arc, every smudge, every oddly stretched galaxy image is a signature of the invisible. Space is, as it turns out, the only place where funhouse mirrors help with physics. There's something profoundly human about this kind of discovery. We're creatures who depend on light to see, and yet we found a way to use that same light to learn about what lies beyond it. We read the universe by its distortions, like archaeologists brushing dust off the faint outlines of a fossil. And the deeper we look, the more we realize how elegantly the cosmos keeps its balance. The seen and unseen intertwined in ways that are both mathematical and poetic. Gravitational lensing reminds us that even when light bends, truth doesn't, it's just refracted, waiting to be untangled. The arcs and rings scattered across deep space images aren't imperfections. They're the universe speaking in the language of geometry and gravity. And if you trace that language far enough back, following the light as it stretches across billions of years, you find that the same gentle distortions appear in the earliest glow of the cosmos itself, the faint afterlight of the Big Bang, still rippling with the fingerprints of the dark. Long before there were stars, galaxies, or even atoms as we know them, the universe was filled with a hot, dense fog of particles and light all tangled together. It was a place without transparency, a cosmic dawn before dawn. Photons, the particles of light, couldn't travel freely because they were constantly colliding with electrons and protons in a restless dance of energy. If you could have stood in that ancient fire, you wouldn't have seen anything at all. The universe wasn't dark, it was blinding. But as it expanded, it cooled. And when it cooled enough, about 380,000 years after the Big Bang, everything changed. The free electrons settled down and joined with protons to form neutral hydrogen atoms. For the first time, light could travel unobstructed, racing outward across space like ripples spreading from a stone dropped into an infinite pond. That light has been traveling ever since, stretching and fading as the universe expanded, until today it reaches us as a faint, nearly uniform glow known as the cosmic microwave. Background, the oldest light in existence. If you tune a television between channels and see a bit of static, a tiny fraction of that noise is the whisper of that primordial glow. It's everywhere, surrounding Earth, flowing through every corner of the cosmos, gentle echo from when the universe took its first deep breath to the naked eye. The cosmic microwave background looks perfectly uniform. But when astronomers began to study it in detail, they discovered something extraordinary. There were tiny variations in its temperature, mere thousandths of a degree scattered like faint freckles across the sky. These delicate ripples were the fingerprints of the early universe, and they contained a map of everything to come. In those small differences, we can read the first hints of cosmic structure. The slightly denser spots were regions where gravity had begun to gather matter. Over billions of years, those spots would grow into galaxies, clusters, and the vast filaments of the cosmic web. The slightly lighter areas would become the great voids between them. It was as if the universe had left us its baby picture, showing the first stirrings of everything we see today. But here's the remarkable part. Without dark matter, those ripples could never have grown large enough, quickly enough, to form galaxies. The visible matter, ordinary atoms, were still tightly coupled to light at that time, buffeted around like dust in sunlight. Every time it tried to collapse under its own gravity, Radiation pressure would push it back out. Dark matter, on the other hand, didn't care about light. It wasn't part of the electromagnetic chaos. While the visible matter was bouncing around, dark matter was already pooling quietly under gravity, forming the invisible wells that would later catch the ordinary matter once things cooled down. In a very real sense, dark matter gave the universe its head start. It was the quiet scaffolding upon which everything else could gather. Those first faint ripples in the cosmic microwave background weren't just fluctuations in temperature, they were the gravitational fingerprints of dark matter already shaping the cosmos. Astronomers have been studying that ancient light for decades using satellites like COBE, WMAP, and Planck. Each mission has painted a more precise portrait of the early universe when plotted as a map. The microwave background resembles a mottled sphere of subtle color shift threads where the radiation is slightly warmer, blues where it's cooler. These variations may look like random noise, but they're anything but. They reveal the universe's exact recipe. How much of it is ordinary matter? How much is dark matter? And how much is the mysterious dark energy that drives its expansion from those ripples? Scientists have calculated that only about 5% of the universe is made of atoms, the stars, the planets, everything we've ever touched or seen. About 27% is dark matter, and the remaining 68% is dark energy, a force we understand even less. Those numbers aren't guesses. They're measured directly from the cosmic microwave background, written in the subtle pattern of its fluctuations. It's as if the universe left us an accounting ledger carved into light dot to imagine what those ripples mean. Picture a perfectly still pond just before sunrise. The first faint light of morning touches its surface, and you notice small circles spreading outward, soft and quiet. Each ripple marks a moment when the water remembered a disturbance, a leaf dropping, a fish breaking the surface. Now scale that image up to the size of the universe, and you have a sense of what the cosmic microwave background shows us. Those ripples are the universe remembering its own beginning, and they're astonishingly precise. The spacing between the peaks and troughs of those fluctuations tells us how fast sound waves traveled through the early plasma, which in turn depends on how much matter and radiation the universe contained. The pattern is so well defined that it's like listening to the echo of a bell and inferring the shape of the bell itself. From this, scientists can tell not only what the universe was made of, but how it has evolved ever since. Perhaps most poetic of all, this ancient light is still arriving. Every second, photons that have traveled for nearly 14 billion years wash over Earth, carrying with them a memory of the cosmos before the first star was born. They pass through you, through the atmosphere, through the ground beneath your feet, endless waves from the time when everything began. It's humbling to realize that every image of a galaxy, every map of cosmic structure, and every simulation of dark matter's role in shaping the universe all trace back to this faint background glow. It's the baseline of existence, the quiet hum beneath all cosmic music. Even the tiniest irregularities in that glow are crucial. Without them, nothing we see today would exist. If the universe had been perfectly uniform, gravity would have had no starting point. Matter would never have gathered, stars would never have ignited, and the night sky would be a smooth, eternal fog. The tiny imperfections, those 1 in 100,000 differences, the reason you can look up and see constellations at all. Imperfection, in this case, is the origin of beauty. Every time we measure the cosmic microwave background more precisely, the universe's story becomes clearer. And every time we look deeper, the role of dark matter grows more evident. It was the silent partner, guiding structure before light could speak for itself. The galaxies that now shine across the sky are simply the glowing outlines of the shapes dark matter drew first. The cosmic microwave background is, in many ways, the universe's autobiography written in faint radiation. It tells of a hot, dense youth, of slow cooling, of invisible forces at work long before light could roam free. And though the universe has grown immeasurably since that time, those early ripples still echo through everything that exists, through every star, every planet, and even through us, the next time you glance at the night sky. Remember that you are seeing the end of a long story that began in that ancient light. The faint ripples on that cosmic pond became galaxies, stars, and life itself. The echo from the beginning still hums softly all around, carrying the quiet memory of how darkness gave birth to the light. By the time the universe was a few 100 million years old, the fog had cleared, the cosmic microwave background had faded into the distance, and darkness once again ruled the sky. But this was not an empty darkness. It was full of invisible structures already forming beneath the surface. In that unseen landscape, gravity had been busy sculpting the future. Dark matter had begun clumping long before the first stars ignited. Freed from the push and pull of light, it drifted and gathered under its own quiet gravity, forming enormous halos, vast, roughly spherical cocoons of invisible matter. Each one was a gravitational seed, a potential home for the luminous galaxies yet to come. If you could have seen it then, you'd have witnessed a universe filled with ghostly spheres, completely dark yet brimming with potential. Into these halos, ordinary matter began to fall. Clouds of hydrogen and helium gas cooled as they collapsed. As the gas sank into the gravitational wells carved by dark matter, it began to swirl, compress, and fragment. And where the compression became strong enough, the first stars flickered to life, igniting in the dark like embers catching and kindling in a poetic sense. Dark matter was the potter, and the visible universe was the clay. It shaped, supported, and steadied the form while never showing its own hand. Without the guidance of dark matter, this process would have been slower, messier, and far less efficient. Galaxies might never have formed in such abundance, and the night sky would be a lonelier, emptier place. The halos formed a kind of cosmic hierarchy. Small ones appeared first, merging over time to create larger and larger structures. When two halos collided, their dark matter passed through almost unhindered, combining to form a new, more massive home for galaxies to grow within. Meanwhile, the gas, collisional and chaotic, heated up, shocked and cooled again, sparking new bursts of star formation over billions of years. This dance built everything from small dwarf galaxies to the giant spirals and ellipticals we see today. Every galaxy you can see, including our own Milky Way, sits at the heart of one of these invisible halos. The stars and planets are just the visible frosting on a vast dark foundation. The halo extends far beyond the luminous disk, reaching hundreds of thousands of light years into the surrounding void. Most of its mass lies where light cannot go. Simulations of the universe beautifully reveal this pattern. When astronomers model the growth of structure over cosmic time, they start with nothing but dark matter particles and gravity. Out of this simplicity, halos emerge spontaneously, clustering and merging in intricate ways. When gas physics is added to the model, the luminous matter naturally gathers within the dark scaffolding, forming galaxies that look strikingly similar to the real thing. It's as if the universe builds from the shadows outward, the dark matter setting the mold, the light filling it in. It's a strangely comforting idea. For all our focus on light, stars, nebulae, and glowing galaxies, the universe's true architecture belongs to the unseen. The halos are like invisible hands shaping clay in the dark, guiding where galaxies may grow and how they will evolve. Even the grand spirals of the Milky Way owe their grace to this hidden influence. Without the stability of its dark halo, the delicate arms of our galaxy might unravel over time, the stars drifting apart like leaves in a breeze. Dark matter's gravitational pull not only gathered gas, but also determined the rhythm of star formation. In dense regions where halos formed quickly, galaxies became crowded and bright, burning through their gas in rapid bursts of star birth. In quieter corners, where halos grew slowly, star formation stretched out over billions of years, producing galaxies with gentler, more drawn-out histories. The cosmic web, with its filaments and nodes, acted as the highway system that connected these halos. Gas flowed along those filaments, feeding the growing galaxies like rivers nourishing valleys. Each halo was a basin at the junction of those streams, collecting material and turning it into light. The result was a universe both orderly and alive, a grand interplay of gravity, motion, and time. Even today, the relationship between dark matter and visible matter continues to shape galaxies. The halos dictate how fast galaxies spin, how massive they can grow, and how they interact with their neighbors. When galaxies collide, it's their halos that meet first, merging long before the stars ever do. The luminous mergers we observe, those spectacular collisions captured by telescopes, are merely the visible surface of a deeper, darker event happening quietly beneath. Astronomers have even found hints of dark matter's influence on smaller scales. Tiny dwarf galaxies orbiting giants like the Milky Way appear to be held together by dense knots of dark matter. Without it, their weak gravity wouldn't be enough to prevent them from being torn apart. In that sense, dark matter acts like a cosmic glue, preserving delicate structures that would otherwise dissolve. If dark matter didn't exist, the universe would be unrecognizable. The early gas would have remained evenly spread, unable to condense quickly into stars. Galaxies, if they formed at all, would have been smaller, rarer, and dimmer. The night sky might contain only a few faint smudges of light, rather than the hundreds of billions of shining galaxies we see today. The dark, it turns out, made the light possible. Understanding what dark matter is, not just what it does, has become one of the most important quests in all of science. We can trace its fingerprints in the way galaxies move, the way light bends, and the way the universe evolved, but we still don't know what it's made of. It's like hearing footsteps echo through an empty hall without ever seeing who walks there. Scientists have spent decades trying to pin down the identity of these invisible particles. If dark matter isn't ordinary matter, not protons, neutrons, or electrons, then it must be something entirely different. The possibilities are both fascinating and frustrating. One of the most popular ideas for many years has been the existence of WIMPs, weakly interacting massive particles. These hypothetical particles would have mass, giving them gravity, but would interact with ordinary matter only through the weak nuclear force, one of the most subtle interactions in physics. If WIMPs exist, they would drift through you and through the Earth right now. rarely, if ever, colliding with a single atom. The theory fits neatly with what we know about how the universe evolved. In the early hot cosmos, WIMPs would have formed naturally, interacting just enough to reach the right abundance we observe today. Their gentle, gravitational presence could explain the large-scale structure of the universe almost perfectly. But so far, despite enormous effort, we've never detected one deep underground, in laboratories shielded from cosmic radiation and noise. Scientists have built detectors designed to catch the faintest hint of a WIMP. These detectors are filled with materials like xenon, germanium, or argon, elements chosen for their stability and purity. If a WIMP were to collide with one of these atoms, the interaction would create a tiny flash of light or a subtle vibration, a whisper from the dark. For years, experiments like Lux, Xenon, and Pandex have listened patiently for that whisper. Each upgrade made the detectors more sensitive, the instruments quieter, the shielding thicker, and yet nothing definitive has appeared. The silence has been instructive, though each null result narrowing the possibilities, pushing scientists toward new ideas. If WIMPs aren't the answer, perhaps the universe is whispering through something even stranger. One alternative candidate is the axion, a hypothetical particle, so light and elusive that it could drift through stars and planets without ever being noticed. Ixions were first proposed to solve a problem in particle physics, not cosmology, but they happen to make an excellent dark matter candidate. If they exist, they would behave more like a collective wave than individual particles, subtly altering electromagnetic fields in ways we might one day measure. Other possibilities are more exotic still: sterile neutrinos, hidden sector particles, or even entirely new forms of matter that don't fit into our current understanding of physics. Some researchers wonder if dark matter might not be a single thing at all, but a family of different particles, a dark ecosystem with its own subtle interactions and rules. There are even ideas that challenge the need for dark matter entirely. A few physicists have suggested that maybe gravity itself behaves differently on cosmic scales, that Einstein's equations, elegant though they are, might need modification. These theories, called modified gravity, or MOND for modified Newtonian dynamics, attempt to explain galactic rotation curves and cluster motions without invoking unseen mass. But while they can account for certain galactic behaviors, they struggle to explain the full range of cosmic evidence, especially gravitational lensing and the cosmic microwave background. For now, the balance of evidence still points strongly toward dark matter being real, not a flaw in gravity, but a genuine, invisible component of the universe. The challenge is simply to find it. That search continues in many directions. Some experiments, like those deep underground, hope to detect direct collisions between dark matter and ordinary atoms. Others look to the skies, searching for indirect signs, perhaps dark matter particles, occasionally annihilating one another and producing faint gamma rays or other exotic signals. Observatories like Fermi and instruments on the International Space Station have been scanning the heavens for such clues. Meanwhile, particle accelerators like the Large Hadron Collider near Geneva try to create dark matter in the lab by smashing particles together at tremendous energies. If the collisions occasionally produce invisible particles that carry away energy and momentum, it could be a sign that dark matter has briefly flickered into existence before slipping back into the dark. So far, nothing conclusive, but every test tightens the net. The pursuit is both maddening and magnificent. To chase something invisible, you must rely on inference, patience, and creativity. The work demands years of silence and a deep tolerance for uncertainty. Yet beneath that quiet persistence lies an astonishing faith, the belief that nature, no matter how secretive, will eventually reveal itself to those who keep asking the right questions. And there's a certain poetic symmetry in that. The universe has been shaped by something that never announces itself, something that works without light, noise, or contact, just gravity, just presence. The scientists searching for it mirror that same patience. They too work mostly in the dark, waiting for the smallest sign, trusting that even the quietest truth can still be found. Whether it's a WIMP, an axion, or something no one has imagined yet, the discovery of dark matter's true nature would be one of the greatest revelations in human history. It would connect the smallest scales of quantum physics with the largest structures in the cosmos. It would show that the universe's missing mass, the shadow that gives shape to the stars, is not a mystery to be feared, but a piece of reality we have only just begun to perceive. And so, as we come to the end of this quiet journey through the unseen universe, let's linger for a moment in the stillness. The story of dark matter is at its heart, the story of everything that holds the cosmos together, the quiet balance between what shines and what does not, between what we know and what remains just beyond reach. When you look at the night sky, every pinpoint of light is the visible surface of something deeper, anchored by the unseen. The galaxies drift like lanterns across a sea of darkness, but it is the dark itself that steadies them, that keeps their fragile harmony intact. It's a reminder that the most powerful things in existence rarely demand attention. They simply are. Perhaps that's why dark matter captures our imagination so deeply. It's not just an astrophysical puzzle. It's a reflection of something profoundly human, the desire to understand what lies beneath the visible, to reach beyond what light reveals. For centuries, we've followed that instinct, building telescopes, sending probes, mapping the stars, and now searching the dark. Every discovery expands not only our view of the universe, but our sense of what it means to exist within it. Dark matter might never glow or collide or shout its presence, but it leaves traces everywhere in the motions of galaxies, in the bending of light, in the pattern of the cosmic web. Those traces are like footprints in fresh snow, silent but undeniable. And we, standing in that vastness, are the ones learning to read them. It's a strange kind of beauty, one that doesn't rely on brightness or spectacle. It's the beauty of form without color, of pattern without sound. A cosmic architecture built not from what we can see, but from what we can sense only through its influence. In that way, dark matter is both elusive and intimate. We may not see it, but we live inside it. The next time you walk beneath a clear night sky, take a moment to look not only at the stars, but at the spaces between them. Those dark stretches aren't empty. They're full of quiet structure, full of the same substance that has guided galaxies since the dawn of time. You are, in some deep and literal way, surrounded by it, connected to the same invisible framework that holds the Milky Way and every distant cluster of galaxies together. And though we may never touch it, the search itself is enough. The effort to understand what lies beyond the reach of light is a testament to what makes us human. Our refusal to accept that the unseen must remain unknown. We are, after all, creatures made from stardust and driven by questions. So rest now, knowing that the universe is vast, mysterious, and whole. The light that reaches your eyes tonight has traveled for billions of years, crossing through the invisible fields of dark matter, guided by its gravity the entire way. Every beam of starlight that touches you has been shaped by what cannot be seen. The cosmos doesn't divide itself between light and dark, between known and unknown. It simply exists, luminous and invisible, together. And you are part of that same fabric, held in place by the same quiet force that binds the stars. Let that thought settle over you like a blanket. The dark is not your enemy. It's the reason the light can shine. It's the calm between the notes, the gravity that gives the stars their dance. Close your eyes. The universe hums softly in the background, the ancient music of creation still playing beneath all things. You are safe in its rhythm. You are part of its symmetry. You are made of both the light that glows and the darkness that endures. Sleep now within the web of the unseen. The stars will keep their watch. The dark will hold everything in place. And the cosmos, vast and quiet, will go on endlessly, beautifully, and at peace.